So we wrap up the photometry topic by talking about the CCD equation in a very short video. So this CCD equation is the relationship between the signal noise ratio versus various kind of noise sources. It can be driven from two different ways. Okay? One is through the Mutata and then Fowler, the paper published in 81, considering each different noise source directly. The second method is we can actually drive from this the from the from the earlier the expression of the source count from I think recorded in ADU, which is the summation of all the sources within the aperture, subtracted by the sky contribution. In this case, the sky is the general inclusive terms of every unwanted. And in here, there actually the bottom expression is various kind of the mathematical expression of flat field, the pixel to pixel sensitivity variation, linearity correction, dark current, and then the read noises. So that derivation we can ignore, but actually one thing that actually we can think about is this CD equation is the attempt to express the behavior of many different the noise sources as a function of exposure time. So let's just express this final recorded source count, okay? Final recorded count from the source in terms of exposure time. To do so, we are actually introducing some constant, the count rate from the source. So the your object is producing certain number of per second. So that is actually expressed in n star dot. So it is the n sub dot, n dot of the sub star. So the total recorded count from your source over the duration of exposure time of t can be expressed as the n dot multiplied by the t. So then first term in this CCD equation is basically the square root of the source count. So you can actually immediately recognize that as first term is Poissonian noise. And then let's just skip the second term momentarily and then come back later. Last term, which is actually that the it's simply just proportional to the number of pixels, but there is no proportion the dependency on the exposure time. This is the read noise term. So read out noise is happening regardless of any the length of the exposure. So whenever that actually read out the digital detector, we always have some sort of read out noise. So read out noise, the term is the third one. And then the second term is the true noise from the sky. This is not the inclusive term. This is a true noise from the actual nighttime. And we can likewise to the source count can also express the count from the sky as in terms of count rate. So count rate from the sky, and also that actually dark current. Okay, dark current is also can be expressed in terms of dark current rate. So this second term is the sky dark current. Is Both of them are actually proportional to the exposure time. Okay? So overall, that actually first term is the Poissonian noise. Second term is the sky and the dark current. Third term is the readout noise. So we can consider the three different limiting cases where there actually each one of these noise terms actually come down. So let's think about the case that actually that only the first term is the dominant noise source. That means sky and dark current is negligible and readout noise is negligible. In that case, that is actually the case of that actually when we observe bright source. So then let's just take the log on both sides. second term and the third term on the bottom is actually eliminated, and overall that actually on the right hand side 012 and dot t. So taking the log on both sides, you can actually see the log of signal to noise ratio is is basically one in terms of actually the log of exposure. The log of signal to noise ratio is the one log of t. Okay? So and then because the log signal to noise ratio is expressed on the x-axis, just by rearranging this, log of t is basically 2 log of signal to noise ratio. So this the the line in log plot has the slope of 2. So when we observe the bright source, the Poissonian noise is the only dominant term, and then because of the fast slope that actually that the signal to noise ratio is picking up rapidly with the exposure time. Then let's think about the second term, second case. When what is the situation that actually the sky or the current is dominant source? So because the Poissonian noise from the source cannot be dominant, so that means we are observing faint source, not the bright object. And that case that actually the readout noise is negligible compared to sky. So that means sky background is bright. Okay? The sky background is bright. That means we are the observing at the long wavelengths where the sky glow dominantly. So this means actually in the long wavelengths of near infrared domain, or maybe we are actually so the predominantly they're actually just talking about the red. There is no such the realistic observation case that where the dark current is the only dominant noise. So the instrument builder is actually they try their best in design phase so that actually the dark becoming the only the dominant noise don't actually really have realistic or the dark current dominant case. So usually is the sky is dominant case has the some contribution from the dark current, but the sky noise and then dark current noise sometimes comparable, okay? Or usually the sky noise is larger, more dominant. So generally we actually press that such case limited the case of observing faint source in the long wavelengths. Then first term is cancelled, the second term, and the third term is actually negligible. Then overall, again, that actually this the log of relationship, log of signal to noise ratio, proportional to the same slope, 2 times log of t. So we will have the same slope, but because that actually that top we are observing the faint source, so that actually that source count on the top is actually less compared to the case of the bright source. So for the given the exposure time, it produced the smaller signal to noise ratio. The sky limited observation case has the same slope of 2 as in the bright source case, producing the smaller the signal to noise ratio for the given exposure time. Then lastly, when the observation is dominated by the readout noise, can we actually think about the realistic case of the readout noise dominant case? Yes, when the dark current and the sky noise is almost negligible, that means we are observing in the visible wavelengths. So remember that actually night sky to our eyes is pretty dark. It means the noise is actually negligible. And usually CCD is the suffering much less dark current issue compared to the infrared array. The second term in the optical domain where the CCD is usually negligible. By observing faint star, the Poissonian noise is actually negligible as well. Then log of signal to noise ratio is directly proportional to log of P. So the slope is actually at 1 instead of slope of 2. Starting with the shallower, the straight line in low time versus low signal to noise ratio. So that's the readout noise limited case. But gradually building up this, the, the source count, we actually that actually the source count, the Poissonian noise that actually becoming the important term gradually. Starting with the slope of 1, but gradually change the slope of 2. So this is the readout noise limited observation case. And this is happening usually when you observe a faint source in the optical domain with this instrument.